liquid nitrogen testing of an integrated reaction control system. And I have three names of authors: Anson Koch, I hope I'm pronouncing that correctly, Hannah Cherry, and Cameron Hines.
So my name is Anson Cook, and I'll be presenting with Hannah Cherry here regarding some liquid nitrogen testing that our team did in the summer of last year at Marshall Space Flight Center. Cameron Hines was, he no longer works at Marshall, but he was also on this team, so we wanted to make sure that he got credit for this as well. Just quick little overview of what we'll go over, a little background about IRCS, some of the challenges that we tried to address, the way we set up our testing to go over that, and then the results and conclusions and lessons from our testing effort. Background on what IRCS, it's the same propellant that you use for your main rocket engines on a space vehicle is also used for your reaction control system thrusters. It's intended to reduce system complexity and also reduce your attitude control system mass so that you only have one fluid system and you don't carry extra tanks for storable, traditional storable propellants. So I'll pass it off to Hannah for her to discuss some of the challenges about this.
All right, can you hear me?
Yeah.
All right, cool. So some of the challenges we needed to address with this, storage, because the main propellant system propellants are stored at much lower pressures than what we needed to figure out a way to get those up to pressure. The CFM and the operational kind of run into each other because you're going to get a lot more heat leak in your RCS operations when you're pumping your cryogenics through to cool in your, chill down, there we go, your hardware prior to actually firing your RCS system. And next slide. LN2 testing started roughly in late 2019 in the Propulsion Research Lab, or 4205, at Marshall, specifically in Lab 108. We were on track to test in spring of 2020, which obviously did not happen. We used CTB2 tank was used as the LN2 supply inside of 108, and that was filled up from a dewar outside. And our recirculation loops with our simulated thruster pods were set up outside of 108, so in the wonderful Alabama summer. Again, we paused buildup due to COVID and resumed in January of 2021. I was allowed to come on site, and then Anson and Cameron were allowed to come on site a little bit after I started coming in for hardware building. And we completed our testing in August of last year. So here is a early shot of the thruster pods. This is before we insulated. You can see the solenoid valves, 4 on each of the thruster pods. You can't really see the other thruster pod in the distance, but it's back there, I promise. So each one of those solenoids was controlled and specifically through the programs for some of the later test series in this. Yeah, you can see some of the sensors, and you can, yeah, it's an even better picture. This is during the test. You can see the barrels we used to catch the LN2, so we weren't just spilling liquid nitrogen onto the concrete outside of the lab. We used spray foam and Armaflex for insulating the system. It's a little bit of better shot of both of the thruster pods that were used. We got the BPR here, that pressure regulator. This is mid-test. You can see the lovely ice buildup we got on the BPR. And then that line that follows out of the BPR and goes up, that goes back inside the building and into CTV2. Here's a little bit more detailed shot of one of the thruster pods. You can see the two solenoids with pressure sensors a little bit upstream from them, and then the dump line, and you can see the recirc line that goes around the solenoids that allowed us to chill everything in before we actually started the fire testing. And one more shot mid-test. Got a lovely ambiance going with the gaseous nitrogen that was boiling off. And the next slide, we have a system schematic. If you can see the dotted line that runs through the middle of the testing, that denotes where we had hardware located inside versus outside. So we started with CTV2, and from that tank, we ran through the pump, and then it went through a pass-through in the wall, out into the tanks, or the thruster pods, excuse me. And got both of our thruster pods on there, the recirc line, and the BPR is located right before we go back into CVT2. And a chunk of the stuff that is in the upper right-hand corner of this schematic is all facility hardware that we tied into to be able to get pressurization and air required to run everything. So our test objectives, we needed a characterization of the ambient heat load on CVT2, because prior to this, there wasn't like a good recent heat load characterization on it. So we needed to do that before we got going. GTO 2.1 was standby mode. So essentially we were going to be recirculating the LN2 in the system and chilling everything in, making sure that we had adequate pump speed and everything from the oversized pump that we were using for the system, as well as being able to maintain the quality of the fluid. So making sure that we could get liquid nitrogen flowing throughout the entire system, just doing very basic flow tests. And then GTO 2.2 and 2.3 were the active mode. So that was when we were actually simulating thruster fire. We had a couple of different setups for like how quickly we would cycle the thrusters on and off, how many thrusters we would cycle, that kind of thing, and try to figure out if we could maintain inlet pressure, flow rate, and quality during those testings, as well as investigate the water hammer and see how it propagated through the system.
All right, so I'll go over some of the data we gathered in the test series. So the first one for characterizing the heat load on the tank, our approach to that was to measure the venting flow rate and also get a measurement of the bulk temperature, which is kind of all of these thermocouples kind of squashed together. Down here is the liquid, and then this is just showing, a nice kind of steady state stratified ullage. So we did that at a number of fill levels, and waiting for the ullage pressure to settle that to a steady state mode, we were able to then get a calculation of the total heat leak into the tank, and even separate it by what's going into the liquid, what's going into the ullage. And we repeated this for a number of fill levels. So this is for the 72%. Did it also at 90%, and measured about 1,000 watts of heat coming in through this method. The next step was to characterize, we have our basic quiescent tank getting some, atmospheric or just, heating from the ambient environment. And we want to see what is the additional heat that comes when you start running the pump. So we ran the pump at a series of increasing speeds from 12 hertz all the way up to 43 hertz, and we're able to start picking up this heating trend as the testing went on. So measuring the, we kind of showed the ambient heat here, and then the heat rate from different speeds as the pump's running to sort of get an idea of, what is the heat load that's going to happen just from simply running this pump. And we especially noted that as the pump starts running at higher speeds, we start getting quite significant heat loads compared to just the ambient heat. One thing to note, the pump that we had on hand in the lab was oversized compared for sort of the reference mission that we had built our test series for. So, the pump that we, when we acquired the pump, we were more designing this concept towards a manned Mars landing, which called for much larger flow rates. So that's kind of one of the reasons our heat load gets so high here. Moving on to the next test objective, GTO 2.2, we wanted to characterize system performance under steady state thruster firing. So this would be, the driving case for this would be a course correction burn that's performed by an RCS. It's, some steady level of thrust over some predetermined amount of time, and we want to simulate that in our little hardware analog here. So one thing to note, this is kind of a zoom in from our schematic earlier. We used the data from these two instruments just downstream of our back pressure regulator to get our fluid properties for this test. And we could, first of all, see that if we just started firing, we didn't really get into actual chilled in steady state conditions until about 200 seconds into running the test. For this next test sequence, this one, we initiated the test sequence at 70 seconds, and then everything steadied out at 140. So this one only took about 70 seconds to reach steady flow conditions. After that, we did a pulsing mode. So this would be analogous to making a landing during like the final phase, the landing descent phase of the mission. And we had a number of different pulse profiles that varied everything from pump flow rate, how many thrusters are actually firing, what's the total bypass flow, how long are the thrusters firing for, and also how frequently are they firing as represented by the duty cycle here. And so we have this is just a subset just showing you for the test cases from this matrix, but this is just to kind of show you the different parameters we were tracking. To keep our test matrix manageable, we did this under constant pump speed and tank pressures. We wanted to cover a wide range of potential RCS operational scenarios, but not necessarily didn't really see a large need to get the same sort of variety in tank pressures or pump speed. So this is showing kind of a representative test profile. So this particular test was firing 2 thrusters at 40 millisecond pulses with a 5% duty cycle. So this is just to show you what the firing profile looks like. This is the, so one of the things we wanted to characterize was the inlet pressure to the thrusters. How does that respond to the sort of rapid opening and closing of these valves? So we were able to then measure a 135 PSI slump when it opens, but then a 60 PSI spike once it closes. So you can see the green is the pressure that catches the slump, it closes, and then it bounces back up, gives the 60 PSI spike. Another thing we wanted to look at was what happens downstream from the thruster pods back at the BPR inlet. So we see this same, this is the thruster command here, and we see a slight delay for the pressure oscillations to actually work their way through the system. And the big thing we note is that the pressure spike magnitude does attenuate along the path of the flow. So it's attenuated down to about 30 psi from compared to 60 from before. This is a comparison of the flow meters. So this is, how much does the flow change during these valve transients? And we're seeing that it ends up being a pretty tolerable flow change. It wasn't anything that was threatening the pump or the stability of our system. This is also a graph of the pump inlet pressure, and we see that these spikes are very small, so just the mass of the liquid in the tank is attenuating things even further. And then in the discharge pressure, it's harder to see the correlation here, but we're still just showing the stability of the system, so that even when the thrusters are firing, we're not seeing, the pump is not working against too much chaos. So for another comparison, this is a different test case we selected, and this one has more thrusters firing for longer durations. So this is a 6 thruster case, 200 millisecond pulses with a 25% duty cycle. So this is one particular solenoid, but all 6 solenoids are opening and closing according to this pattern here. We see, again, a similar magnitude of the slumps and spikes, but this is one where we noted that the magnitude of the slump was decreasing as the test proceeded. So even over this little 4-second window we're showing here, the slump goes from, it's about 130, drops down to, you lose maybe about 40, 60 psi there on the slump magnitude. We do also see smaller magnitude of these same pressure transients at the BPR inlet, including that same small delay for the pressure transients to propagate through the system. The flow meters, now, this is one where we had to divert some amount of flow through the recirculation path for the sake of system stability. So the recirculation path would basically be downstream of the pump, and it's basically a path just to bypass the thrusters and send it back to the tank. So this is what we're seeing in flow meter 1's the total flow. I believe flow meter 3 is capturing some of the recirculation flow, and we do see some larger changes in flow rate here as we go to more thrusters under longer pulses. Even with these longer pulses and more thrusters, we fortunately did not encounter cavitation during pump operation, and this was one of our major concerns as we were designing the systems. We were unsure if all of the different valve transients downstream would end up causing cavitation at the pump inlet. And fortunately, we were able to avoid cavitation through our system as it was built. And in the same way, there is a measured response to the thruster firings, but again, nothing that the pump couldn't handle. As we were also going along, we wanted to measure water hammer using some dynamic pressure transducers. So we had them located, one of them just downstream of the pump, and then I believe we had 2 more, which I believe I forgot to mark on this slide. Yes, one right at each thruster pod inlet. So that's that one there, and that one right there. So what we're seeing here is over this short time span, the same test series I was showing previously, we are able to actually see the beginnings of a pressure wave forming as a result of the valve opening. A little harder to get the same result here, and in hindsight, that was because we had not designed our data acquisition system to get high enough sample rates to really capture this effect. So we are, we're aware of that as a lesson learning going forward. If to get better water hammer data, we make some modifications to this on the on future work. Same deal here, looking at the water hammer at the other thruster pod, being further downstream, it has a little less action going on in the pressure transients. Looking at the water hammer at the pump discharge, this ended up being a lot more noticeable, especially with the opening and closing. This last part here, we did some pre-test modeling and had ended up getting some test results that varied quite a lot from our model. And as we were going through this work, we had not had a chance yet to actually update our models, but we at least wanted to include a comparison just for completeness here. So we had a model of our test system in GFSSP that predicted an 88 PSI drop on valve opening and a 457 PSI rise on valve closing. This ended up being a huge concern for us, but fortunately the actual pressure spikes were about an order of magnitude lower, and we had similar order of magnitude at least on the slump predictions. So we need to kind of go back to the drawing board on our model and take another look at what was causing that. Similar thing here on the comparison for this test, looking at just what was happening at the BPR. This was showing we got pretty good agreement on the slump and not great, but still workable agreement on the pressure spikes there. So I'll pass it off to Hannah for the conclusions here.
Yep, and Hannah, if you could wrap it up, and we're a little bit over, but I think you've just got a couple slides.
Oh, yeah. Yeah, so like Anson said, our test data collection sample rate wasn't quite high enough to record some of the peak pressures in order to, get a higher fidelity view of what was going on with, pressure waves and possible water hammer stuff. We need to address our issues with our model and go back and work on that some more. And we ended up having lower flow rate through the bypass line. The issue is more pronounced at the thruster inlet and not the BPR. So, those could be some of our issues that we hope to address moving forward. In summary, we were able to successfully measure the tank heat load on CVT2. Our entire team was able to get some good operational experience with cryogenics and restart pump. We were able to measure the additional heat from the pump, again, due to some instrumentation failure. We're not 100% certain on it, but we were able to get measurements, so that's good. We were able to increase our TRL level for the IRCS concept to TRL3. And moving forward, we've got a digital valve that could be used to replace the BPR that's being worked on by ER14. And Joey Hackison in EV42 is working on an algorithm to control the digital valve in our pre-existing system. We would like to research gear pumps and possibly select one for procurement because of the need for having a smaller pump for future work. We're going to continue analyzing the series data to get all of the good information out of it that we can. We will be adding water hammer characterization as dedicated objectives for any future tests. And we'll add objectives to characterize the ability to control magnitude of slumps and spikes, pressure oscillation, decay time, and other relevant data points. Lessons learned, always check your flow meters, always check your instrumentation. We had a few issues during collection because of malfunctions with some of our instrumentation. Definitely always use a correctly sized pump for your applications. Make sure you're shielding cables in the presence of high voltage power, and always include extra time, more time than you think you need for a system shakedown in your test schedule. I think that's it. We'd also like to thank Cameron Hines, Joey Hackison, Kevin Peterson, Mike Allison, Katie Webster, Tim Smith, Carlos Diaz, and Tommy Reed for all of their help during this process.